You feel the strike before you fully comprehend it. A massive transfer of kinetic energy shoots up the rod as a heavy predator inhales the lure and turns hard. The rod bows deeply under the strain. The drag screams, and then, without warning, the tension vanishes. The line goes completely slack. The fish escapes. Most anglers search for a familiar mistake, a poorly tied knot, a fray in the line, bad luck, or simple human error during the fight. But in many of these encounters, the culprit is the very hardware anglers trust most. The treble hook uses an over-engineered geometry that, while designed for contact, creates significant mechanical compromises during the fight. Human intuition suggests a simple equation. 3 sharp points offer 3 times the security. It looks inescapable. For generations, this design has been the standard for maximizing the chances of a hookup. Physics, however, ignores intuition. The interaction between a hook and a predator's mouth is governed by the strict laws of vector mechanics and material resistance. By attempting to cover every angle, the treble hook introduces structural flaws. It is an over-engineered system whose multi-directional geometry can actively work against its ability to hold on under dynamic stress. In the violent, close-quarters chaos of fighting a heavy fish, added hardware complexity often creates vulnerability rather than strength. The physics of a lost fish begin the moment you set the hook. When you pull back on the rod, the tension traveling down the line must convert into piercing force at the end of the rig. On a single hook, all pulling force concentrates into a single point, maximizing pressure to pierce the mouth. But on a treble hook, that tension divides across multiple points. Spread thin, the pressure at each tip drops, lacking the energy to break the tissue. This force division prevents the points from driving past their barbs. The result is a shallow, precarious seat that can be dislodged by the slightest shift in momentum. Once the strike ends, the fight begins. The fish reacts with violent kinetic energy, thrashing and shaking its head to throw the lure. The treble hook is forged from a single, rigid piece of steel. Its 3 prongs are fused at fixed angles, so the structure cannot adapt when the fish changes direction. This rigidity initiates the fulcrum effect. The point that managed to catch superficial tissue now acts as a stationary pivot in the fish's jaw. As the fish moves, the thick, unburied shank and the remaining free-hanging points project outward. They instantly become a rigid mechanical lever arm attached to that pivot point. The treble hook's geometry has transformed the hardware. It is no longer a piercing weapon, but a mechanical lever working directly against the angler's tension. The conflict of forces is extreme. The angler applies heavy linear pull in one direction, while the fish thrashes laterally in the other. This conflict creates intense torsional torque. The fish's lateral movement twists the rigid shank against the embedded point. As the fish shakes, this torque causes the sharp wire to slice laterally, wallowing out a massive cavity and destroying the anchor's stability. With the anchor point compromised, the torque acts like a crowbar. It physically pries the hook backward until it slips out of the widened hole. The treble hook doesn't slip out by accident. Its own design generates the exact mechanical force needed to tear itself free. The biological aftermath reveals the extent of this mechanical trauma. Examining a lost catch often shows large linear tears and wide cavities where the rigid hook leveraged itself through the tissue. Sometimes the hardware itself fails. Anglers often retrieve these lures to find their forged steel hooks visibly bent or warped by the intense torsional strain of the fight. These seating problems are even worse against armored predators. When facing the thick, interlocking scales and hard, bony structure of an alligator gar, the hook lacks the concentrated pressure to break the surface. These failures are a predictable outcome of the multi-point design. By dividing the strike force across multiple tips, the hook lowers the localized pressure precisely when a deep, bone-piercing set is required. In high-stress physical environments, structural rigidity can guarantee a catastrophic mechanical failure. Contrast the treble's rigid constraints with the physical efficiency of an inline single hook. Because there is only one point of contact, it can achieve the clean, deep anchor seen here in the jaw of this giant trevally. A single hook pivots freely on a single rotational axis. This neutralizes the torsional leverage that pries treble hooks loose, allowing the hardware to move with the fish. This unhindered pivot allows the single hook to maintain a deep, bone-locking grip regardless of how the predator thrashes. When absolute survival is on the line, stripping away over-engineered complexity is often the only way to find true strength. Pure simplicity is the most effective tool for the job.